our recording. Yes, and Go, could you please start your demo day?
Yeah, sure. Hi, everyone. I hope everyone is doing okay. Hi. So let's start. The topic of this demo is the architecture of the fiber reconciler. I will try to explain everything in minor detail, so you guys will not have any questions, but I will answer all of your questions by the end of the session. Okay, so here is the architecture of the fiber reconciler. So who am I? I'm Magardish Minasyan. You can call me Muggle. I'm a front-end developer here at Provectus. I'm very enthusiastic about this topic because when I was researching about this topic, when I was understanding and comprehending how everything was working under the hood, I realized the complexity that was and the research development process that was put into this in order to create this data structure, and all of those new front-end frameworks are doing this advanced data algorithm structure approaches to give the user a best smooth user experience. And for me, I realized, oh no, maybe the front-end frameworks are going to the next level, and we have to understand how they are working if we want to actually try to optimize them or use those algorithms to our advantage. So that's what I'm trying to do. Before we start, I'm going to give you a disclaimer like last time. This is an algorithmic dive. This will not teach you to write a better React code, and you will see more diagram than code. I'm sure many of you that participated in the last demo, you will see some, okay, is he using the same structure that he was using last time? Maybe he doesn't know how to code, that's why he's using diagrams and everything. No, I just try to use it with diagram because we have a very limited time frame, and in order to understand it with code, we should actually spend some time on it, and you will not remember it. But when I explain to you with diagrams, you will actually, this thing will be imprinted in your memory, and you can actually check the code later on while referring to the diagram and get a better representation for it. You can repurpose the algorithm. The core algorithm that I'm going to explain is very independent from React. So when you understand the core algorithm, you can take this core algorithm, modify it, and use it in your application, whether it is a backend application or a front-end application or a mobile application, whatever suits your need. But just that 30% additional thing that I'm going to explain is just icing on the topic. You just add it in order to make it work in the React, but the 70% are very core, and it will be, you can actually repurpose it for your need. And I will not use a term without explaining what it is, because this is an algorithmic dive. I have a lot of, there are a lot of data structure that I have to explain in order for us to reach our conclusion, but I will not say a term without explaining what it is. So we are all on an equal footing here. Let's move on. So what awaits us? In order to understand the current algorithm, we have to understand the old model, the old algorithm, and its downfalls, right? Why React actually chose to write this new implementation, and it took them more than 1 year to write it and spend some research development money on it. If we don't understand what was the bad thing that was happening in the old algorithm and its downfalls, we're going to understand some data structure. I know some of you already know this, like stack, call stack, linked list, etc. But I'm going to explain it so, as I said before, we're going to so we can all be on an equal footing here. And we're going to rearrange a tree as a linked list in order to recreate the stack. This single line, I know it's hard to pronounce and even hard to understand. This is what the algorithm is doing, and I will explain it in detail as we move on. And we can understand then, after how we understood how we can recreate those core algorithms, we're going to understand how React is actually using this in order to make some updates on the code. So what was the problem? Okay, when dealing with UI, the problem is you have too much work to do executed at once, and it will cause some animation drop frames. Well, for example, when you have a function and you are executing a function and it is a long function and it's taking the V8 engine or the browser engine a lot of time to execute this function, it will not be able to go and execute an animation, and it will cause an animation drop frame, and thus bad user UI, and thus less users using your websites. So what was the solution? The solution, the newer browser and React Native actually implemented an API that was addressing this exact same problem. And what was this API? In the browser, I know the name, it request idle callback. It's basically telling the browser is telling you, okay, I don't have any much work to do. You can do your work. You do your work, and then browser say, oh, stop, I have to do some animation. You will stop the execution of your code, and you will go say to the browser, okay, continue your work. The browser will do the animation and come back to you during its idle state and continue the work on your code. Thus, it will not cause the browser to have an animation drop frames. Thus, a much better, smoother UI. So in order to use this API, we have to have a functionality that we can pause an execution of a certain process, and we can then continue in the future. Like I said, when you are doing some process and you are working and the browser comes and say, okay, I don't have any much, I have to do some animations. You will say, just let me finish this work. You pause it. You say to the browser, okay, go on, continue your animations. And the browser goes and do the animation. When it finishes, it will come back and you can continue from the point that you left. So your functionality, your algorithm should have this ability to pause the execution. But the React Old Recursive algorithm, some people call it the virtual DOM or the stack reconciler, but it's much more preferable to call it the stack reconciler, and I will explain why, does not actually let you do this exactly, does not actually let you pause the execution. So what to do? React actually implemented this new data structure called the fiber tree in order to let them be able to pause the execution of a certain process and go let the browser do the animation and then come back, continue the execution of that fiber structure. So the browser created a new API that lets you solve these animation drop frame issues. In order to use it, you have to actually be able to pause the execution of a certain function. The old algorithm was not letting you do that, but the new algorithm with the new implementation does help you do that. So what's the solution? As I said, the fiber structure, like a definition, is the re-implementation of the stack specialized for just React component, and you can think of it as a singular virtual stack frame. And now I will explain to you what does those words mean. So here is a simple animation. The old stack reconciler and the new fiber reconciler. As you see here, the old stack reconciler has some animation lags because it was not using the new APIs that the browser implemented, and it couldn't do that because you couldn't able to pause the execution of the function. But the new fiber algorithms, because it has that ability to pause the execution, it was giving us a much smoother UI. So I mentioned that I will explain everything that I said. So let's start with just one simple definitions, and we will work through it. So what is a fiber node? Each individual component in React Tree called a fiber node. Every fiber node has some work to do, like getting the children, doing some effect, and performing manipulations. There's this funny joke actually. When I was actually presenting this to our learning development team that helped me very much with this presentation, they realized that getting children and doing effects, what are you talking about? Are you doing some malicious stuff? I said, no, they are programmatic words that actually means the children are actually the leaves of the tree, and the effects are the DOM manipulation that you are doing on them. because when we use our programmatic words, we don't realize that there are some people that can interpret those words differently. So that's why I want to clarify that those children and effects are meant programmatically. So going to the next, let's go to our first data structure. It's called the stack. A stack is a last in first out data structure. So basically, I think maybe all of you encountered the stack in your life. For example, when you are ordering a book, books on top of each other, and you don't have nice shelves to put them, you just order them one by one, and you remove the top one, and then you remove the second top one, and etc. That's what the stack in. The last one that goes into it, it's the first one that goes out from it. So the stack has two functions. The first one called push, the other one is called pop. So I'm pushing a number onto the stack. So what happens? You are putting that number onto the last element, the first element of the stack. And then I am pushing a second one. So I am putting the second element on top of my first element. And then I am putting Mago, because you can actually put anything you want in the stack, any type of data structure like strings, arrays, objects. That's why I will put, let's say, my name, Mago. I'm putting Mago. So I'm pushing Mago onto the stack frame. And then I am popping it. So I am removing which one? The last element from the stack, from the list, and it will return to you its value. So when I remove the pop, it will remove Mago from the stack. And then I can, like I did before, like I can push Provectus into the stack, and then I can remove it by calling the pop functionality again. So some of you are wondering, why is he explaining something that maybe we never use in our daily life? And the next thing, we use the stack in order to create something called the call stack. Call stack is the way of the program, the compiler, the code executor, to keep track of what's calling what and where it is, and what is the accessible variables for that particular procedures. So when the compiler executes your function, it actually puts it into something called the call stack, and that call stack actually controls everything related to your execution function and what variables and what kind of things that is accessible to that data structure. Let me demonstrate to you with an example. Okay, you have a procedure one. Procedure one, imagine a procedure one is a function. Procedure one is being called. Okay, when the procedure one is being called, we are pushing into the stack three stuff. The first one is the parameter of the P1. The second one is the address, return address of the P1. And the third one is the local variables that should be accessible in P1 function. So these three stuff together are called the context of P1. So we are calling a P1. All of those things get pushed into the call stack. And then this P1 procedure in it is calling another procedure called P2. And then because this procedure is being called, we are pushing all of those things that is related to P2 onto the call stack in order for us to know where we are. So we are pushing it. And then the P2 doesn't call anyone. He is returning us a value. When it's returning a value, we know, okay, the function execution is finished. So we no longer need those data that we push onto the stack. Now we can do what? We can actually pop them off the stack in order to not be cluttered with them. And then we are popping it off the stack because the P2 is being finished. And then P1 is calling another function called P3. And as we did before, we push it onto the stack, we put the variables, and then P3 is being finished. We are popping them off the stack, and then thus P1 is being finished, the execution is being finished, and then we are popping off the local variables, the return address, and the parameters from the call stack. So this is basically how the compilers, the browser, the V8 engine, and everything that control where the execution of a certain function is, knows where they are. When you go to the browser, there is this stack navbar that you can go through the stack thing and check out where your function is and what's calling what, and etc. and etc. And since our algorithm works with recursion, I will try to demonstrate another example with recursion onto the call stack. And simple recursive function that we first learn when we start doing recursion is the factorial. Basically, a factorial is a simple function that is calling n times a factorial of the number below it. So factorial in itself is calling itself again with a lower number. So we are calling factorial 3. Factorial 3, we are pushing it onto the call stack, the variables, and the factorial 3 is calling factorial 2, and factorial 2 is calling factorial 1. And then we are pushing factorial 1. And now we have the value of factorial 1. Factorial 1 is being finished. We are returning the value of factorial 1 to the factorial 2. And then we are returning the value of factorial 2 to factorial 3. And then we are giving you the result of factorial 3, and the job is finished. So basically, call stack is a good way to keep track of the recursions as well. So where does the React comes into the play? So React Old Recursive Algorithm structure. Basically, React has a single function called walk. It calls on the tree. So what is a walk? Imagine you have a tree and you want to paint the tree with some white paint. I know it's not a good thing to do. It's not environmentally responsible, but it is just hypothetical example that I'm trying to demonstrate. So you have a tree, you're gonna walk all the tree. So basically the task is to paint all of the tree with a single color. So how you actually do it? You do the work, like you go to the root of the tree, you paint it, okay? And then you see all of its children, you see how many branches there are. Okay, from the root, I have 4 branches. I will go on each branch. So you will loop through all of the children. You will go on each branch, get the child, so get the first stuff from the branch, and do the walking on it again. So it's a recursive function that lets you draw or paint a tree on the whole with this recursive algorithm. And let me try to demonstrate it much better with the diagrams. For example, we have this data, this tree. A1 is the root. It has 2 children, B1 and B2. And B1 has 2 children, C1 and C2. So we are calling walk on A, right? So A is doing work. So we are pushing A onto the call stack and we are logging it. And I just put the login, just imagine a console log in the function in order to keep track of who is calling who. Then I'm getting all of the children and I am looping through each children, right? So I am looping through B1. B1 has some work to do, pushing onto the call stack, logging it. And then B1 has a child. So I am looping through the child. I am pushing it into the call stack and I'm logging it. And then C1 does not have any children. So like factorial 1, the job is finished. So we're going to put it in green. We're going to remove it from the call stack because we no longer need the variables and the parameters of C1. And we're going to move to the second child of the B2. So we're going to do the job. We're going to push it on the call stack. We're going to log it. And then the job is completed. And we remove C2 from the stack. And now, since all of the children of B1 is finished, technically it means that B1 is finished as well. So we remove the B1 from the call stack. And then the same thing, since we called the iteration on A, all of the children, B1 is finished, we move to B2. And then you do the work on B2, you push it onto the call stack, and then you log it, and then the job is finished. You remove it from the call stack, and thus A is finished. This was how React, with its recursive old algorithm, used to iterate through a tree. This was a very typical thing to do in most of the textbooks. They had a tree, and the first thing that comes to mind, just iterate it recursively. It's much easier to write it down. But it turned out that this algorithm had, because it was actually controlled by the call stack of the browser, you cannot actually pause the execution of the function. So React has to either do the whole recursion or not do it at all. So you didn't have any ability to pause it. So what's to do? Basically, they wanted to create this logging that I demonstrated below with another structure from scratch that they wrote in order to have the full control over the call stack. And when you have the full control over the call stack, you can actually pause it and then let the browser do the animation and come back and return to your job being done as well. So how this new algorithm works? Basically, React re-implemented this tree into a linked list data structure. Technically, a linked list where it's not technically a linked list here, but it's very similar to it. You have a node and you have a reference to your next and previous component. So the parent will have a reference to its first child because the parents only need to know the first child, and the child will have a reference to its first child and its siblings. So, and when you are the last sibling, all the children will have a return address to their parent. So the parent will have a reference to his first child, the child to the next sibling. Since this sibling is the last sibling, it will have they both will have a return address to A. But B2 has children, so it will have a reference to his first child, and the same goes over again. But how do we actually iterate over this tree? And the answer is very simple and very creative. So you do the work on A, you go to A, you ask him just one question. Do you have any children? Do you have a child? He will say, yes, I do. Then you will ask him, just give me your child. And you will push the A into the virtual call stack, because this is not an actual call stack. We are not calling any of the functions. We are just iterating it with a loop structure. You are putting A into the call stack, virtual call stack, and we are logging it. And then we are asking, do you have any child? It will return to you B1. Okay, then we're gonna ask B1 the same question. Do you have any child? He will say, yes, I do. I have C1. We're gonna do the work on C1, and then we are going to ask him, do you have a child? He will say, no, I don't. Okay, we're going to say to him, okay, your work is done. We're gonna put you in green, but we're gonna ask you, do you have any sibling? He will say, yes, I do. Okay, give me your next sibling. So since the work is done and we got the next sibling, we can actually forget about C1 and start working on C2. The same thing goes over. Do you have a child? No. Okay, so your work is done. Do you have a sibling? No. When you don't have any sibling, it means that you are the last child. So with that return thing that we had to your parent, you will go back to your parent, and thus your parent work is done as well, since your parent did render all of the children. So technically the parent work is done. So when the work was done, what we were going to ask him, do you have any sibling? Yes, he did have a sibling, B2. We are getting the sibling. We are asking him about his children. He doesn't have any children yet. And then the work is done for B2. And then because the work is done, you don't have any siblings as well, you just go to the parent component. And then we are just checking if it is the same component that we started before. It means that, okay, I did all of the iterations and I am back to my parents. Amazing. Let's go to the thing. The thing is, when you explain something like this with animations and everything, it's like you remember that scenario when you are doing some kind of work for a month or so, but then you are showing it to one of your friends and he's saying, okay, is it just this? And you're saying, yeah, I've been working 1 month. And the animation was exactly like this for me. It took me more time to do the animations than to understand the algorithm. Okay, let's move on. Okay, how all of this is actually linked to the React again. So with this abstraction layer, as I said, because React implemented all of this logging functionality as the same as the React or the recursive algorithm, when we had the same iteration, React has the full control over this over this stack. It means that React can actually keep in memory the current working the node in the tree and go back, let the browser do the animation and come back and continue working on that tree and then finish the tree and then do the rest. So because of this new algorithm, it is giving us a full control over the stack. It means asynchronous rendering. So how is all of this is linked? The basic algorithmical structure is very simple. So you have a looping function. It asks just two questions. Do I have time? You are asking the browser. Do I have enough time to do the process? And does my next component exist? And what was the next component? The next component was either do you have a child, or do you have a sibling, or go back to your parent. And yeah, that's the next component. So if this expression says no, you don't do anything, because either you don't have any time or you don't have any work to do. But if this expression is true, you perform your unit of work. And what was the unit of work? It was rendering the children, doing all of the processes, rendering the children. And then when you perform your unit of work, you get the next unit of work, either the child or the sibling or your parent. And you get your next unit of work and you ask the same question again and again and again until you don't have the next unit of work or you don't have any time left. So with this algorithm, I think we can construct mentally how React is able to pose the execution of the function and then continue it whenever it wants, and thus allowing the browser to not drop any animation frames. So congratulations, it's not finished yet. We are 70% through, but the core algorithm was mentioned before. So everything that is following this is related, how all of this is linked to the React, is linked to the diffing algorithm, is linked how React actually to paint something onto the screen. So let's go through it. How to connect our previous knowledge, the core algorithm that we learned about with React. So let's try to make a thought experiment, because I drew a lot of stuff. I didn't want to draw a button. So let's imagine we have a simple button component, button written in your JSX, right? So what's happening under the hood? So you are writing JSX. The JSX is being turned into a React element. Before version 18, when you used to import React, it was React.createElement function that was returning this instance. But nowadays, it is a function called _JSX, and this one is returning the same React element. So it's basically the same thing. So this React element will be turned into a fiber node, and then the fiber node will be turned into a fiber tree. So when you write JSX, it will be turned into React element, and that React element will be turned into fiber node and then fiber tree. And thus, at the final thing, you have a fiber tree, your current fiber tree. So we have two cases to investigate now. We have the initial rendering, where you actually React DOM.render something, and you have the update case. The initial rendering is when actually you create the fiber tree. You don't have anything yet. You just go through the children with the algorithm that I said. You create the fiber tree, or during the update, you mutate your fiber nodes. Why the React chose the mutation fiber nodes rather than creation? Because the fiber node was a structure that was actually keeping in it a lot of variables, and it was having some memory allocation problem. So they thought about actually mutating it was much efficient than creating a new instances. That's why they chose the mutation nodes version. So what's happening during the update? So during the update, React is creating some of the work in progress nodes that are being changed. And when the work in progress is done, when the work is being done, when you are returning to your parent, you are flushing all of those on the screen, flushing all of those changes onto the screen. Yeah, I know flush is one of those words that I mentioned before. It's used in programs as well. So other thing to talk about, React did very justly when it actually renamed in the hooks, it used use effects instead of use lifecycle method, because the effects approach was much efficient. So what are the effects? How the React team is defining effects? What are those? Effects is anything that you can mutate the DOM, or you can perform some lifecycle methods. So, and since applying effects are a type of work, a fiber node is actually a very good mechanism to keep track of those effects, those mutating the DOM, those lifecycle methods. We understood that during the diffing, React how is iterating the tree, that worked with fiber nodes. And now we are understanding the DOM mutation and the lifecycle method are also implemented by the fiber nodes, because the structure, we can take the effects as a type of work, and we can do the same thing that we did before. So why the React updates are so fast? Because instead of iterating the whole tree after the diffing, React creates a linear list of fiber nodes. And instead of iterating the whole tree, it will iterate just this single fiber list that will, because the quantity is very small, it can iterate it very fast. And instead of iterating the whole tree, it will iterate just this elements and can do it very effectively. Let me show it to you in an animation that we will understand together. Imagine this tree, the root is A, and we are changing something in C2. So maybe some text or properties. And when the diffing happens, it will realize, okay, C2 is very different from the C2 that we did render before. So it does have some change. And we know that we call the change effect. So it will ask the question, who was the last effect? And since there was no effect before it, C2 will link itself with a reference with the root element. So we are linking the first effect, the C2, with the root element. And since the work here is done, what we are supposing to do, we should go back to the parents, and the parents will see, because the children was changed, I have to trigger some lifecycle method or something. So we have a type of effect on B2 as well. So B2 will ask, who was the last effect? The last effect was your child, C2. And then it will link itself to C2, and then it will go back to A. And since the A was the root, it will create a single linked list like this: the root, the first update, and then the second update. And during the commit phase, instead of React iterating through all of those trees, it can just iterate over those three elements and can apply the changes onto the DOM in a much more efficient way. So this is the last thing that I'm going to explain. So how does the general reconciler, the change detection algorithm in React works? It is actually separated into two distinct parts, the render and the commit phase. The render is actually the diffing algorithm. The render figures out what did change into the tree. It will do those things with the effects. It will put some flags on it. It will say, okay, this is changed, this is changed, this is changed. But the render is asynchronous, and the commit is actually flushing all of those changes onto the screen, painting them, and the commit is synchronous. And I will explain to you why is this the case. The render phase is asynchronous because the diffing can take a very long time, and you can actually pause the execution, and it is a type of work, and you can pause the execution, you can let the browser do the animation, and you can come back and figure out what did change. But the commit, we have the commit is actually all of your work in progress. You have the work in progress tree, the current tree, and the effects that you did create. You have to apply, you have to make your work in progress tree, your current tree, and you have to apply all of those effects onto the DOM. And since you are applying all of those effects onto the DOM, you have to do it in a single commit. Otherwise, it can view some button and you will have a very jagged UI, and your UI will look broken because you did update it in bunches. And that's why the commit phase is synchronous, because you have to do all of your DOM updates in a single bunch, in a single batch. But the render phase, the diffing phase, because it was figuring out what did change into the tree, you can actually make it asynchronous and let the browser do the animation. So, and the commit phase is just basically just one function into the source code. It is a commit root function that's calling a commit before mutation life cycles. It's all of those life cycles in the class components that I don't remember anymore. And most of them are deprecated now. You are calling those before mutation life cycles, the function. And since this is asynchronous, you are calling them. And then you are committing all those host effects. Like I said, the text list that we are creating, you are applying all of those changes into the DOM. And since all of the changes into the DOM are being applied, you can then call your commit all life cycles like component did mount, use effect, and etc. And that's it. Conclusion, it is over. So what have we learned? Some new fancy data structures. We can recreate the stack so we can have the full control over it. Inner knowledge of how React change detection mechanism works. And Fiber is not mysterious at all. Yeah, it's done. If you guys have any questions, I will be happy to answer them after I drink my water.
Yes, thank you, Go. So guys, you can unmute and ask your question, or another way, you can type your questions in our chat.
Or maybe I should ask questions.
Yes, so we have maybe we have some reaction from Vagan. Maybe you want to comment or would like to ask some question. You can unmute.
Just clap.
Oh, okay. Thank you. Okay, guys. So thank you, Go. Thank you for your interesting topic. Thank you for your interesting speech. So we will share with you guys this presentation and the recording of this meeting in our general channels. And also, if you will have some another questions, you can join to about front-end channel as an example and ask your questions in this channel. So thank you, Go. See you on the next demo day. Bye bye.
Bye.
Thank you so much.
Thank you.
Thank you. Bye.